Hello AP Calculus students, Mr. Record here. Another video over the applications of differential equations. Let's jump right in. It's an advertising problem. It says 4 months after it stops advertising, a manufacturing company notices that its sales have dropped from 100,000 units per month to 80,000 units. If the sales follow an exponential pattern of decline, what will they be to the nearest unit after another 2 months? Well, the key in this problem, as with many of the ones that are in this series, is looking at this language. The sales follow an exponential pattern of decline. And that's just a simple way of saying that we can use our wonderful friend, the equation, sometimes we refer to it in our class as KECT, or in this particular case, we could say sales, S, is equal to some constant C times E raised to the KT power. Now, all this is just a derivation of solving the differential equation that I'm writing above, that the rate of change of the sales are directly proportional to the number of sales. And I've got a couple of other videos where I actually work through the differential equation solution of this particular equation and arrive at our S equal CE to the KT. So we're going to start right here, and then we're going to start kind of using some of the information in the problem to figure out what we want. Well, obviously we want to figure out the number of sales after another 2 months go by, but we can't do that while we've got C and K still unknown in the problem. So we look at our first pieces of information, and we know that there was a time when the sales dropped from 100,000 per month down to 80,000 per month, and it took 4 months to do that. So what it's really basically saying is at the very outset of this problem, we're going to define our time to be 100,000. Maybe not use a decimal in an ordered pair there, but we're going to use 100,000 as our sales with T as our time. Now, you could probably see that the 100,000 is definitely going to be the value of C, but if you don't see that, you could just simply plug in the 100,000 in for the S while you plug the 0 in for the T, and you would find out that e to the 0 is 1, and that just produces the C equal to 100,000, which is pretty much confirming our thoughts. So our equation takes on a slightly different look now. It's now 100,000 e to the KT. But our next obstacle is to find the value of K, and that is where this guy is going to come in. And we know that the 80,000 is going to be the amount of our sales when the time was 4 months after it stopped advertising. So we're going to go ahead and let the sales be 80,000, while at the same time we let the T be 4. So now we have an equation that contains the single variable K that we can find. If we divide 100,000 over, we could just call this 0.8. And at this point, we could take the natural log of both sides. And at that point, the 4K would come out in front, right? And we would have a natural log of E. If that's bothering you, I can kind of show you a little bit more slowly what happened on the right side. But you'd have that expression where the 4K is allowed to then come out in front. And then the ln of E here is just going to be 1 eventually. So K is going to be the natural log of 0.8 divided by 4. So that gives us a completely new equation here for our sales. So I'm going to go ahead and write this one out. The sales will be, at any time t, we can dress it up if we like, 100,000 times e to the ln of 0.8 over 4 times T power. All we need to do now is to plug in an appropriate value of T, and we would have our sales. But there's a trick to this question. If we read very carefully about what we want, it says, what would the sales be after another 2 months? So we don't want to plug 2 in for T, because that would give us a very incorrect answer. That would give us the sales 2 months after we decided to launch this new advertising campaign, or stopping this advertising campaign. We want to apply this after the initial 4 months have gone by already. So for that reason, we would want to use 6 for our t. So it's really important that we understand that. Now, there are other ways that you could have worked through this. It is possible that you could have used maybe a different initial value. Maybe you used 80,000 here. If you used 80,000, it doesn't matter. The K value is still going to be the same. It applies to the same situation. But at that point, you could have used 2. It's probably likely that a student wouldn't think to do that, but I want to let you know that it is possible. But in the way that I've set this up, we definitely want to use 6 for K. Now I'm going to pause the video while we open up the graphing calculator and we can type this in and see what our final answer is.